Alright guys, just a reminder, okay, what we're doing today, I wanted to record the instructions just real quick of how to get to Pearson for your next assignment. So yes, you sign into the portal, clicking on Pearson, and over here on your assignment that you have, it's going to be, so let's go to 5th period. You have an assignment due tonight for 5th period, 3/4 is due at 11:59 at night. And this is the other one. Systems in 3 variables. It says lesson 3-5. If we go to the calendar, that 3-5 is actually going to be right here. Let me show you where it's at. So 3-5 is right here. And basically all you're doing is you're copying down notes. So the flipped part of this, your homework per se, that will be due at the beginning of next class. It means please don't start it like 5 minutes before it is due. Please make sure that you have done this way before because there is a lot of notes. That's your homework, okay? Also due next class will be checkpoint 2. Here's a link right here to the thing that you can print off or create a digital copy from your house, but it will be due also at the beginning of class on next time I see you. Okay, so we just did the quiz. Today I have a couple videos to show you. We will also work out an actual elimination example, and this is going to be with a 3x3. And then we'll look at a quick video as far as the foldable is concerned. The rest is just like extra practice. If we get to it, that's good. If we don't, it's not necessarily going to be detrimental because we covered the big parts of today. Okay, so just keep that in mind. Big questions for today are the following. When is 0 a negative number or a negative number an inappropriate answer to a real life problem, or how do I decide how many variables equations a situation needs? Any questions? Okay, so let's go ahead and begin by looking at this video here. We're going to start at 325.
A and the solution B to 1 equation.
Okay, so this stuff right here that you're about to see, is huge as far as understanding the pinnacle of this unit. Okay? So watching it, the 3-dimensional representation, we're going to be doing equations that are involving these 3-dimensional representations. And I'll tell you right now, this is probably one of the most challenging times that you'll have, at least in this first semester, because there's a lot of algebra going on, okay? If you can understand conceptually what you're doing and put all your skills together from what you've learned so far in this unit, it's not that bad at all. But it's if you're behind, you could get further behind very quickly, and it could be frustrating. So please make sure that we are very diligent with asking questions, but at the same time, not losing the skills that we've built. Here we go. So 320.
Systems will be flipped off by looking, saying every set would not be aligned.
Here we go.
The equation 0 equals C cannot be a linear equation. So let's create a simple linear equation in x and y by setting A to 0 and B to 1. This eliminates x from the equation. If we set the constant c to 3, we get the linear equation y equals 3. Since the values of x are no longer constrained by the equation, x is free to take on any value. The graph of this equation therefore consists of every point whose y-coordinate is 3 and x-coordinate is any real number. The set of all these points is a horizontal line 3 units above the origin. Likewise, setting b to 0 and a to 1 eliminates y from the equation. If once again we set c to 3, we get the linear equation x equals 3. Now, since y is free to take on any value, the graph let's try the same thing for a linear equation in 3 variables, setting the coefficients of all but one of the variables to 0. Let's start by setting a and b to 0 and c to 1. This eliminates all the variables but z. If we set the value of d to 3, we get the linear equation z equals 3. Since both x and y are free to take on any value, the graph of this equation consists of every point in three-dimensional space whose z-coordinate is 3 and x and y coordinates are any real number. The graph of this equation is therefore a horizontal plane, 3 units above the origin. If we set a and c to 0 and b to 1, all variables but y are eliminated from the equation. And setting d to 3, we get the equation y equals 3. Now, since x and z are free to take on any value, the graph of this equation consists of every point whose y-coordinate is 3. The graph of this equation is therefore a vertical plane, 3 units to the right of the origin. Likewise, if we set a, b, c, and d to 1, 0, 0, and 3, all variables but x are eliminated, giving us a graph which consists of all points with an x-coordinate of 3. The graph of this equation is a vertical plane, 3 units in front of the origin. Now, what do you suppose would happen if we set the coefficient of only one of the 3 variables to 0? For example, let's set the z coefficient to 0 and the x and y coefficients to 1. This eliminates z from the equation, but leaves the variables x and y. Now, if we set the value of d to 3, we get the linear equation x plus y equals 3. Let's ignore z for the moment and plot this equation on the xy plane. This gives us a line which intersects the x and y axes. Every point on this line is a solution to the equation x plus y equals 3, where the z-coordinate of every point is 0. But there are more solutions than this. All points on any line where x plus y equals 3 are solutions to this equation, regardless of the value of z. There are an infinite number of lines like this, one line for every possible value of z. Since z can be any real number, all these lines together create a plane. Each point in this plane corresponds to a solution of the linear equation x plus y equals 3. The graph of a linear equation in 3 variables will always be a plane when graphed in Cartesian coordinates, assuming that the constants a, b, and c are not all 0. Any plane which corresponds to the solutions extends infinitely in all directions. Depending upon the values of a, b, c, and d, the plane may lie in any position and orientation. We have seen that systems of 2 linear equations in 2 variables can be represented graphically as lines in the Cartesian plane, and the solutions of these systems correspond to the points where the lines intersect. In systems of 3 linear equations in 3 variables, the equations are represented as planes in Cartesian space. Each plane may be oriented at any angle and positioned anywhere in space relative to the other planes. Since each plane graphically represents the set of solutions to one of the 3 equations, The points where all three planes simultaneously intersect correspond to the solutions which simultaneously satisfy all three equations. These points, therefore, correspond to the solutions of the system. In the next lecture, we will look at different ways in which three planes can intersect in three-dimensional space, and thus different types of solutions which can exist for a system of three linear equations in three variables.
Alright, so that's that one. Let's go now to summarizing it all together.
Hello, I'm Professor von Schmohawk, and welcome to YU. In the last lecture, we saw that just as the graph of a linear equation in two variables creates a line which extends infinitely in both directions, the graph of a linear equation in three variables creates a plane which extends infinitely in all directions. Since the graph of a linear equation in three variables is a plane, a system of three linear equations in three variables can be represented as a group of three planes. Each plane may be oriented at any angle and positioned anywhere in space relative to the other planes. Since each plane represents the set of solutions to one of the three equations, any point which simultaneously falls on all three planes corresponds to a solution which simultaneously satisfies all three equations. That point will therefore be a solution of the system. In this lecture, we will look at different ways in which three planes can be oriented in three-dimensional space, and different types of solutions which can exist for a system of three linear equations in three variables.
So he's about to talk about what kind of answers you can have. Whether it's one, whether it's no solutions, whether it's infinite solutions, but he's going to do it in 3D, okay? And he's going to compare and contrast them too.
Systems of two linear equations in two variables can have three types of solution sets, depending upon the ways in which the lines are oriented in the Cartesian plane. If the lines have different slopes, then they must intersect at a single point, and the system will have a single unique solution.
That was your quiz, pretty much.
If the lines are distinct and parallel, then there are no points of intersection, and the system has no solutions. And if the lines are identical, the two graphs coincide, intersecting at an infinite number of points. The system, therefore, has an infinite number of solutions. Likewise, systems of three linear equations in three variables can have a single unique solution, no solutions, or an infinite number of solutions, depending on the ways in which the three planes are oriented. Let's consider all the possible ways in which three planes can intersect or not intersect. We will number these planes 1, 2, and 3. One possibility is that no two planes in the system are parallel, and all three planes intersect at only one point. In this case, the system will have one unique solution. A second possibility is that two of the planes are not parallel, and so their points of intersection form a line. If the third plane intersects the other two along this same line, then the common points of intersection for all three planes are represented by that line. The system will therefore have an infinite number of solutions corresponding to every point on the line. The third plane does not necessarily have to be distinct from both of the other planes. If the third plane is identical to one of the other two planes, then the points common to all three planes are still represented by the same line of intersection, and the system will have an infinite number of solutions. An infinite number of solutions will also exist if a system consists of three identical planes. In this case, any point which lies on one plane is common to all three planes. The system will therefore have an infinite number of solutions corresponding to every point on the plane. In addition, there are several orientations of the plane which will result in a system with no solutions. Anytime two distinct parallel planes, there can be no solution. Since distinct parallel planes have no points in common, regardless of the orientation of the third plane, there can be no points which lie on all three planes. The third plane can be distinct and parallel to the other two, identical to one of the other two, or not parallel to either of the other planes, thus intersecting both planes. Regardless of the orientation of the third plane, since there are no points in common to all three planes, the system has no solutions. One additional configuration of the planes which will result in a system with no solutions is if the planes are oriented so that their intersection points lie along three distinct parallel lines. Once again, since there are no points in common to all three planes, the system has no solutions. So we have seen 8 ways in which the three planes in a system of 3 linear equations in 3 variables can be oriented. These orientations can create a system with one solution, an infinite number of solutions, or no solutions. These are the same 3 general categories of solutions which can exist for systems of 2 linear equations in 2 variables. Systems in 2 variables have a single unique solution when the 2 lines in the system are not parallel and thus intersect at a single point. Likewise, systems in 3 variables have a unique solution when none of the 3 planes are parallel and intersect at a single point. Systems in 2 variables have no solutions when the 2 lines are parallel and distinct. And systems in 3 variables have no solutions when any 2 planes are parallel and distinct, or when the planes are oriented so that their intersection points lie along 3 distinct parallel lines. An infinite number of solutions exist for systems in 2 variables when the 2 lines coincide, thus intersecting at an infinite number of points. And systems in 3 variables have an infinite number of solutions when all 3 planes either coincide or intersect along a line. Regardless of the number of variables or equations in a system, if the system has one or more solutions, it is called consistent. And if the system has no solutions, it is inconsistent. Likewise, 2 or more equations whose graphs are identical are called dependent, and equations with distinct graphs are independent. Now that we have seen how systems of 3 linear equations in 3 variables can be visualized, in the next lecture we will see how these systems can be solved.
Alright, so we have now covered. You know that the homework is notes and also this linear programming checkpoint 2 due at the beginning of next class. I'm going to show you this quick foldable. It's the paper that you grabbed on your way in. So go ahead and pull that one out. It has like 3 columns and it's about a 3x3 system. Yes, so the question just now was, the Pearson homework is to take notes, okay? So you're going to look at problems 1, 2, 3, and 4, and you're basically going to take notes, and I'm going to look at it at the beginning of class next time in your binders to make sure that you did take those notes, okay? Yes, it will be for a grade. Real quick on the linear programming, guys, just in case you don't already know this, the checkpoints are all cumulative of 1 daily grade. So 1 homework assignment is all 3 checkpoints. So like the first one I think is like 36 points or something like that, according to the rubric. The second checkpoint is a certain amount of numbers, but they all add up to 100, which is equating 1 homework assignment. But because of that, you don't want to blow it off because let's say you don't turn it in. I can't give you feedback on something that you haven't turned in, okay? But when you do turn it in, I can then answer questions or give you feedback of how you could probably adjust or change things or fix things, because the final project and the due date is here on the calendar, is half a test grade. Okay, you want to make sure that you do that very well. I will also be posting that as far as hanging them in the hallway with your name on them. Okay, So what we're going to do now is we're going to watch this quick foldable video just so that you can see, should you choose to put these notes, this page in your notes the way this foldable shows. I mean, it's up to you, especially if you're a visual person. It has a pretty good layout the way it's shown. Okay, so here we go. Here's the video. This is the piece that we're looking at, and the video looks like the following. We want to see a good way to basically view this so that it's understandable. So here we go. And this is optional. You don't necessarily have to put this in your notes foldable wise. But if you're a visual learner, for sure, this does for sure help. So 3x3 systems, and here's the video. So notice, let me rewind just a little bit. So there it is. The top basically is going to accordion fold down. So it's basically 3 rows, okay? And you can start folding it right now to where those horizontal lines, the very bottom one, you're folding like toward you, and that top one you're folding away from you. Okay, so I'll go ahead and play it and pause it. So you see that as it's coming down, you should end up with the solving by elimination right there at the very top. Okay, so I'll do that one more time. So 3 folds, bottom one is folding toward you, the top fold that's horizontal is folding away from you, so that when you fold it down, the solving by elimination is right there, right on top. Okay? And then as you go, please continue to watch. The middle fold, the middle piece is where we're putting this glue, and there's glue in your buckets. And basically you're just trying to glue the very top piece to the middle one. So then you can grab scissors and just cut that fold that you just glued. You don't have to do it, okay? It's just those of you who want to do it, you're visual learners, and it helps you as far as organize notes, and there's some of you out there. Yes, you could add the foldables. I'm not one of those people, but it's all good if you can. If it helps you, please use it. Put it into your notes. So I'll let this play just a little bit, a couple times. Put it in your notes. I'll come by and pick up the trash here in just a bit. I'll let it play one more time just so that you can see it. And you're just cutting them right there, right in the middle, and keeping in your notes. Okay? The better notes that you guys make has a direct correlation with better test scores, better quiz scores. Okay? Because you're organizing your thoughts and at the same time experiencing that organization as you go through. Very difficult to organize and be prepared for a quiz and or a test if you're very unorganized. And then last but not least, after you glue them, you see right here, you are cutting those top tabs, not the very, very bottom, just the one that you glued together, and then it's nice and easily accessible. Okay? Alright, so go ahead and pause the video and give you time to finish that up for a little bit. Okay, so resuming the video, what I'm going to show you now is a quick video that will go into what we're going to do by hand here in just a bit. Okay, so the video will show you what's happening. I'm going to go ahead and stop the video, and I'm going to start it on the next one that you will be able to see a link in the calendar. Okay, I will put this video in the calendar, most likely like right here, and you can see not only what we did in class, but also you can see the link to a practice problem. Please use this, okay? Because this is like the intro into quote-unquote the most difficult part of this unit, okay? Alright, so let's go ahead and stop the video.